So this video is going to talk about how we can use an Arduino Uno in conjunction with some tangible waves compatible micro modules. Now AE Modular micro modules use a 6-pin header. Let's get that here, and the wonkystuff modules, which this is of course one, only use 2 of these pins. That's the power pins. We've got 5 volts on this corner and ground on the outer corner. Got this breadboard here, and look at that. We've got a ground and 5 volts pre-patched in a sequence. So let's connect that to the Arduino. Cool. And then, like I say, back pin ground. It means we can just plug a drum module straight into that, and now that drum module is powered. Another thing I made for my prototyping is a transition adapter, I guess you'd call it, between the 0.72, 0.76 millimeter round pins for AE Modular to the square pin header for breadboards. So just rapidly sort of soldered together. I put that into the breadboard, and I can now transition between pin headers. So for the Arduino into these, and the AE Modular. So something I was showing at Bristronica quite a lot was there is quite a difference between the 2 pin types. Hopefully you can see that there's a difference in diameter between the breadboard pins and AE Modular pins. The AE Modular ones are somewhat more robust. So what we're going to do is we're going to start from the Blink application. So here's standard Blink app, and if we upload that, we can then see that the LED is blinking. It's 1 second on, 1 second off. So that's on. In this one, the LED is connected to pin 13. So let's connect pin 13 here. An audio connection via here, so via some external wires. So I'm just going to put the ground in there, and I'm also going to put that there. So we have pin 13 pulsing up and down. Like I say, 1 second on, 1 second off. Feed that into the trigger input of the BD55 bass drum, and take the audio out. There we go. So, probably the world's most boring drum machine. Great. Now what? Well, first of all, we don't need that trigger pulse to be high for 1,000 milliseconds. Let's just make it 2. This will make the whole period 1,002 milliseconds. But we can now upload that, and now we can hear that the pulse is happening once a second, and it's already more exciting. 60 whole BPM. One thing that might be nice is to be able to vary the tempo. So I've got one of these potentiometers. It's 10K, which I'll just plug into the breadboard, and then we can connect that to an analog input of the Uno and have some varying tempo. Here we've got the potentiometer wired up. Green is the center wiper, which goes to analog A0, analog input 0. the potentiometer here is connected to the ground and 5 volts. So the voltage when we turn this knob will be between 0 and 5 volts. Let's change our code. We will use analog read, and we'll do that instead of this delay 1000. I mean, this is super crude. That's not a second anymore. Neither is that. So let's get rid of those comments. Now let's see what happens with that. Oh, well, it's sped up. Oh, yep. So we've got tempo control. Oh. Okay. So that's obviously too fast. Let's add a 5 plus that. So it's going to be a little bit slower, but it won't go silly speeds. Okay. Okay. So the disadvantage of doing this with a single big delay is that if you make a sudden tempo change, you'll only hear that change on the next beat. So let's just tweak that slightly. So instead of doing a delay for that amount of time in one go, make a for loop. I, because we always use I, and say that's whilst I is less than that. We're getting I plus plus, and we're going to delay for a millisecond. Now I know I don't need to put curly brackets on every line here because we've got there's only one line after that for loop, but it's good practice. It can get confusing behaviour if you just rely on or don't put the brackets in. So let's try this. Yeah, let's actually write the for loop correctly. So that's much more responsive. So that's all very fine. We've got our let's just turn that down a bit. We've got our very repetitive beat. How do we make that some exciting pattern, some interesting pattern? Well, what we can do is let's get rid of this header because it's not blink anymore. So let's define a drum pattern. We're going to define a constant, which is our rhythm pattern. It's going to be a 16-bit value, and let's call it P, and we're going to use the binary format here. Let's just do 4 on the floor. 1 0 0 0 1 0 0 0 1 0 0 0 1 0 0 0. So that's 16 beats, ticks. We'll put a comment in here to say this is 0 1 2 3 4 5 6 7 8 9 0, 1, 2, 3, 4, 5. Okay, so that's the effectively the beat position starting from 0. So let's just, because it makes things a bit easier, I'm going to remove these and put them into their own function. So let's make a function called pulse. Doesn't take any arguments, and it simply turns the bit on and off again. And we want to use some sort of index to go through this pattern. So let's start with, let's have 8-bit value. It could be any value, any size really, because we're going to restrict its size. Pos for position. So because we're reading this sort of left to right, because that's naturally what we do, we have to start at the left hand side, which is actually bit 15. So if pattern and 1 shifted up by pos, so that means if it's not 0, that bit is not 0, we output a pulse. Otherwise we don't do anything. We can then move our bit position. So we assign 2 pos. The value, if it's 0 we assign 15, otherwise we assign pos minus 1. Let's see what happens there. Well, that's kind of indistinguishable, isn't it? Because it's a regular 4, so it's got slower. So let's give it some interest. Don't know if that's going to be more interesting or not. It's going to be different from just a regular beat. Yeah, there we go. So there we have it. We have a programmable drum machine with variable tempo in the crudest possible way. So what if we want more patterns? So we have to do a bit of electronics here. After a brief interlude, this is changed. I changed the circuit slightly. So instead of taking the audio straight from the output pin of the bass drum, I've made a simple inverting summing amplifier mixer. So I've got an op amp here, because we're dealing with AE Modular. This is a rail-to-rail output. I mean, I'll probably, if you have questions about what all this means, then please write in the comments and I'll do my best to answer. I've used a whole bunch of 10k resistors here. These 3 pins on the right hand side are connected to this red line here via 10k resistors. This red line is connected to the inverting input of the op amp by this orange wire here. The non-inverting input of the op amp is connected to midway between 0 and 5, so 2.5 volts. So that's these 2 10k resistors here being a voltage divider, and then there's some feedback from the output to the inverting input via another 10k resistor. So this is 1, 2, 3, 4, 5, 6 10k resistors, and then I'm taking the output of the this op amp and connecting that to my mixer. So that's what we're hearing now. So not really any different. But now we have 3 inputs to our little mixer, so we can add extra drum modules. We've got 2 more drum modules here, the snare drum, micro snare, and the hi-hat. We should be able to connect, we can connect those all up. That's audio outputs connected. And now we have the triggers connected. So we have pins or outputs 13, 12, 11 and 10 from the Arduino Uno connected to bass drum, snare drum, open and closed hi-hat. So now we need to look into how we're going to drive it. So obviously we've got a single pattern here, and if we want to have multiple patterns, we need to be able to we want to be able to have be able to select any of them. So let's turn this into an array. So we've got let's, rather than having magic numbers, hash define, let's be grand and call it tracks. And then we can define our array to be of size tracks. So this is the bass drum part. Let's move that comment as well. And then we'll have a snare drum part. I'll tell you what, let's turn the bass drum back into its 4 on the floor. And we've got 4 parts. Snare drum. Let's have it on alternate on the 2 and the 4. Closed hi-hat, I think that's next. There's that, and the open hi-hat we can have it in the gaps of the closed hi-hat. So yeah, kick drum 1, 2, 3, 4, snare drum 2, 4, hi-hat doing a little broken 16th pattern, and then the open hi-hat hopefully will be filling the gaps. So obviously that's not going to compile because we've changed the type of P. We're also trying to use multiple pins right now. So let's have another array, which is pin trig pin. So that's also set for the for sized for tracks, and we're using, as I said earlier, 13. So we've got 13, 12, 11 and 10. Okay, so that's the patterns we've got, and we've got the pin that we want those patterns to come out of. So if we have a slight detour into this input here, this pin mode, so we have to specify that the pin is an output. Now we've got 4 pins. So what we can do is so we can make a for loop for all of the tracks. So again, we can use our macro there. And we can set the pin mode of each of those. So trig pin I. So we're going to iterate through the pins, and we're going to set those pins 13, 12, 11 and 10 to outputs. We need to do some stuff here as well. So the loop is fine, but let's move this if into the pulse function. So instead of testing this here, let's put that test in here, and also let's move that. Just tidying things up a bit, really. If our pattern is set, we can, or bit is set, we can set the pin high. Now, one thing, if we haven't already set this high, then, so if it was already low, this will have no effect. So there's no point in putting that inside the if as well. So we've got our iterator again, so we can make another for loop. In fact, let's just copy it from above. Got that. So now P isn't P, or it is P, but so we're indexing it with I. Position is the same variable, so we're looking at if that pin is is high or is set, bit is set, then we need to set trig pin I. And then at the end we need to, of course, do the same. We need to set all of the pins low. No decision to be made, we're going to always set them low. Okay, so does that look about right? Yeah. Okay. There we go. We've got a drum machine. And we can switch up the patterns a bit. Cool. Got some noise coming from somewhere. Not quite sure where that is. So, here we have it. There's a very simple Arduino based drum machine. I expect a lot of people will be screaming at the screen going, "Oh, that's terrible code." Well, it's a demo. Happy to see what other people can do. But anyway, I thought that was just a fun, interesting little experiment. So thanks for watching, and see you next